Okay. Hello. Hi, everybody.
Hold on, hold on, hold on,
This is
hold on a second,
Rajarshi.
Raj. Okay, so hello everybody. So this is our very bold attempt to go live with a seminar, and today we have Rajarshi talking, and is
Okay,
going
so
is
hello,
going to
everybody.
present
So
a
this is
talk on.
our very bold attempt
Hold on.
to go
Ah,
live with a seminar. Yeah, I think you might want to mute the video,
yeah.
the stream.
Okay. Yeah, absolutely. Okay, so I would
Take
say,
two.
so let's start it again. So we are going to do this first seminar on stream, and so today Rajarshi has volunteered to do that. Now the seminar unfortunately is not going to be. I'm not going to be able to collect questions as the seminar goes, but then at the very end, when we finish. Please ask a few questions through the conversation box that you should have on YouTube, and see what happened. So I'll read the question and then Rajarshi will answer to the question. Okay, so without any further ado, I just leave the stage to Rajarshi. Please go ahead.
Okay. Hello, everybody. This is Rajarshi, a researcher in Professor Stefano Zanvito's group at Trinity College. This statement is probably for later for those who are just watching the YouTube video, hopefully. And most of the people currently subscribed who are from our group, they luckily know me. So let's start. So today I'm going to actually summarize last year's work, which was basically search for corrosion resistance for a specific type applications. So here is my outline, which basically is a standard one. I will quickly go through the introduction, and then we'll discuss models of reactivity or models or descriptors for corrosion resistance. Then I'll introduce A-flow database, which is actually a large database of computational material info. After that, we will actually discuss how do we use that database for screening relevant compound for our use. We will also discuss briefly a reaction energy based screening, which is actually a lot cheaper and requires very little information. And then I'll share some ab initio results, after which I will actually sort of summarize. So let's go to the next slide. Okay, I mean, these are some ugly pictures of corrosion. So, I mean, the best way to actually describe corrosion is visual. So the first two, I hope I can actually, I mean, people can see the mouse here. Stefano, if you just nod if you can see the mouse here, mouse moving. Okay. So, I mean, this chain and this pipe, which looks like an artwork of sorts. So these are corrosion's daily life examples. So one is, I mean, you can find a chain anywhere, and these are actually internals of a petrochemical pipe. Where this corrosion is a big nuisance, and we lose a lot of money in industry as well as energy fighting that. However, I mean, our interest is actually a bit different, where you can see a picture taken from Google image. If you just do a Google image search on, corrosion electronics, you see a bunch of interesting things. So this is a representative. So this is a PCB, printed circuit board, and a how to avoid oxidation or corrosion. That is from a user's point of view. I mean, how do you avoid this getting exposed to sort of a corrosive material? I mean, our interest is to find out or search for materials which, if used in these circuit boards, make them a little bit more corrosive. Here is this last figure is an interesting YouTube video, which basically sort of illustrates that one drop of Coke spilled inside a PCB of a Mac computer uh, for just a minute, actually, what kind of damage at a microscopic level it does. So this gentleman actually sort of arranged a tiny hole and a small microscopic camera to look at this tiny part of the circuit board. And after just sort of 1 minute of exposure to Coca-Cola, a drop of Coca-Cola, many of these shiny circuit boards became actually corrosive. So that's a non-trivial problem, and we tried our own bit to actually look for potential compounds that can actually tackle this problem. So a very sort of research sort of summary or a motivation is that we are looking for a non-corrosive materials which are useful for a device application. We're at the moment not interested in sort of petrochemical corrosion, which happens for with usually petroleum, which have a lot of corrosive materials. And those are actually liquid. So we would be generally interested in how to prevent such gaseous corrosion. I mean, you don't every day, make a habit of spilling Coca-Cola on your MacBook. But if you live in in a community or in an area where you have greenhouse gases, a lot of pollution, they tend to actually wear down electronics and not just laptop, a whole wide range of systems. So from theoretical point of view, our starting point is the simplest one. So you look for these possibilities first from elemental metals, then binary alloys, and possibly more complicated compounds. Uh, so that we will be searching for the descriptor uh, of such compounds. The most common thing is some sort of estimate of binding energy of adsorption of some greenhouse gases, or let's say H2S, for example. And even there, the starting point is what is if I get a typical metal surface, what is the binding energy of uh, oxygen adsorption or sulfur adsorption on this surface? And we had started with the first pure 4D transition metal, elemental metals. Now, generally, binding energies depend on the interplay of metal band structure and the chemistry of corrosive adsorbate. However, surface also plays a lot of role. But we were interested in a screening scheme, where we come up with a computationally cheap estimate of binding energy and use it to screen a large database of materials. As we will see, that we have access to such a large database, and we try to actually exploit that. And with that, uh, we hoped to come up with a small number of potential candidate of sort of non-corrosive metals or less corrosive metals, where whatever we can actually find. Now, to for the cheap estimate of the binding energy, so let's look at what are the models. So the simplest model is what called a Nunes-Anderson model, which which looks like the following. So you have a D, you have D band metallic system with the corresponding density of state. They normally nominally have this yellow thick S band and a D band which hybridizes with the adsorbate level. In a Nunes Anderson model, we assume that the bandwidth of this D band is basically zero. So it's just a concentrated large number of levels coupled with adsorbate. With a little bit of algebra, one can actually calculate the binding energy. So the binding energy is the energy of this coupled adsorbate D band system minus the isolated both the systems. And one key parameter in this case, and even for also for the latter models, is the sort of hybridization of this adsorbate level with the D band actually. If we try to actually expand this model, we actually go to Anderson impurity model, which is a more formal, which more formally is written as this expression, where this is tiny Hamiltonian just for the isolated impurity, and then you have and the metal is described by a density of state of a D band and an S band, and they interact. So this is their sort of dispersion individual, and this VKS and VKD typically is the hybridization of the impurity with the S and D band system. Uh, we generally take a simple estimate of Vs, which is typically constant over the 4D transition metal series. Vd, however, depends on the system. And as a function of these, one can actually calculate, it's just a little bit of a pen paper exercise. You calculate the impurity Green's function with this, and assume a semicircular density of state of this, which simplifies the problem quite a bit. From this Green's function, you can get the impurity density of state, and integrating this density of state gives you the sort of energy. And here is how you get the binding energy. So you take the impurity density of state, integrate, get the energy, subtract the energy of the isolated impurity. That gives you the binding energy. And there is, which has potentially an ES part, which comes from the constant S bands. So we use this model as well. And the parameters of these models are basically impurity location, center of the D bands, and these couplings. So we use this model. Uh, uh, so these parameters are actually fitted with an actual ab initio calculations, where one constructs the metallic slabs of the D band metals, calculates the surface binding energy, and sort of uses that to fit the actual data. A small sort of discussions. So here, a very crucial part on which the model performance actually depends is this hybridization VAD of the adsorbate with the metal surfaces. And this has been sort of estimated earlier in NORSCORE and originally in a very old paper of Ole K. Anderson for the 3D, 4D, and 5D transition metals. And this is the dependency. And we generally know the ratio of this with respect to a reference metal such as copper. So we just need to fit a scaling parameter in the model. Once we do that, we actually get uh, a fitted sort of optimal model, which we hope to use for the materials in the database. Now, here is a sort of a model grid of different variant models where, so this is Nunes-Anderson. Uh, Nunes-Anderson plus a Hubbard interaction, if you wish. And these M1, M2 are basically the Anderson impurity model with a small variation in the zero of the energy. And there are possible extensions with U. We will not much focus, we will not put much focus on the Hubbard interaction, as we later learned and the hindsight that the quality of the model does not significantly improve by including such interaction. So these parameters are actually the parameters of these models can be divided into two parts. One, which is a DFT, which actually comes as an input, which is supplied as an input, which is a material or metal specific parameter, because we're calculating the binding energy with respect to a metal. We generally keep the adsorbate fixed. The parameters that we actually fit are typically the properties of the adsorbate, such as the adsorbate impurity level, the constant part of the energy, and a scaling parameter of overall scaling parameter to this VD, which is the ratio of the hybridization of any of these metal compared to copper. So we will generally, we actually tested the Newns Anderson M1 and M2 model and compare their fit. So to do the fit, what we had is with the help of James, who is a PhD student in our group. Uh, uh, so he calculated the ab initio binding energy of different surfaces and different lattice structures of 4D transition metals ranging from yttrium to cadmium. And this we divided into three sets of data. So the surfaces of the native ground states of the crystals, uh, that was one data set of data. The other were surfaces that were forced, that were generated from the forced FCC structure. So where we actually find the optimal lowest energy FCC lattice structure for compounds ranging from, sorry, materials ranging from yttrium to cadmium, and calculated those binding energies and corresponding densities of states, etc. The third set was generated through a scaling argument. So in this first two, we actually used the actual surface density of state, but we also learned that there is an overall scaling which doesn't change much if you just use the bulk band structure. And that helps us quite a lot because calculating surface density of state essentially involves actually setting up a slab calculation, which is quite expensive compared to a bulk calculation. And as we will learn that this distinction does not affect the quality of the model much, and that gave us the advantage to actually explore a rather large set over the Airflow database. So the model depends on impurity level, metal band structure, and the impurity hopping. These are actually available from this literature. Now we'll go to so okay. I think so. This is just an illustrative visualization of chi-square fitting of these models. So we, on one hand, we have this ES, which is a constant part of the energy, uh, the optimal fit for the impurity level for oxygen and sulfur, and the beta, which is the overall scaling. So it provides a rough area. So this is where the optimal parameter set lies, which we use for the model calculation. Once we have that, so the fit model can now be compared with the actual DFT binding energy. Uh, so what we see here is, so these are six panels. So the top three panels, top row is actually the binding energies against oxygen. The bottom is against sulfur. On an x-axis, we have the estimate of the binding energy calculated from these optimal models, which are basically Na, black circles, M1 red squares, and M2 green diamonds. So what we actually learn is that it's hard to say that if a particular model is actually much better than other. However, all of these models seems to perform well. Uh, this is the same figure in which we plot the same uh, uh, model binding energy as function of atomic numbers ranging from yttrium to cadmium. And what we see is that it reasonably describes the atomic binding energy trend. So we can choose these models. These are ridiculously simple and computationally much cheap than an ab initio calculations. So if we have a large database of compounds, we can very quickly calculate this estimate of the binding energy through these models rather than relying on a surface calculation, which is potentially preposterous. So okay, to summarize this part, basically we have now a model descriptor, a fitted model which can cheaply give us a reasonable estimate. It's not the super accurate one, but it is a reasonable estimate which is good enough for us to look for trends out of, let's say, 100 compounds, which 10 are the best candidates. It can certainly help us actually. So we, from now on, we started using the Nunes Anderson because it's the cheapest one, and we can use this. We can use this, and we can also use the M1 and M2. But the quality of our data didn't change significantly, so we stick to the simplest one. And Then we use this model descriptor. The next task is that you actually use this for potentially large compounds. Now let's look at where does these compounds come from and how, I mean, where do we get this data? And I have made several mentions of the A flow. So let's learn what is A flow actually. Now, A flow is a consortium sort of or collaborative effort of potentially 12 universities and PIs in those universities, Stefano being one of them. So this is a large searchable database of basically growing compounds. So the first time I started actually screening compound, that was March 2019. And at that time, it already had 2.5 million compounds and a large number of properties of those compounds organized. Uh, uh, it can be accessed in an interactive way on this URL, but we will actually discuss how to actually extract this data systematically so that you can actually process them. Over the last 1 year, that set became from 2.5 million to 3.2 million compounds actually in over 1 year. So something around 700,000 new compounds or their data was actually added to this list. This is the relative snapshot. The one is March 2019. The right one is yesterday. And as we can see, this provides a way of searching compounds through ICSD number of the compounds, molecular formula, whatever, and it gives you a large amount of information. However, the web-based this website, I mean, is good for interactive use. However, if you want to actually extract the data where you can sort of process or pipeline it through some calculation, you need a systematic way of extracting the data in a non-interactive way. So there are two typical methods available. The Aflow's official support is a REST API, where I mean there is a query server where you actually send a small piece of code which describes what you want to search and how what properties you're interested in, and it filters that search and it actually gives you a list of compounds with corresponding properties. There is an unofficial Python package developed by someone in Professor Stefano Curtarolo's group. However, this one is actually, I found it quite slow for our purposes. So at the moment, I ditched this uh, package. Maybe over the year, it has improved. And in the bottom, you actually see a. I mean, I'm not sure. I hope that whoever watches the video in full HD, he can actually read this figure. So this actually tells you a list of a list of material properties for a given compound. So these ranging from electronic, phonon, lattice, magnetism, a whole lot of properties are actually tabulated there, which one can actually extract. Uh, Now I will just show one illustrative example of how this search actually works. So here on this part, we have this URL, which is the actually the API URL. So this is the server that answers all your questions. However, those questions should be written in a specific language called RESTful API language, uh, which is not super complicated. It supports some regular expressions and a notion of property that you are interested in. So all the properties you can actually put. You can put property with comma, which is unrestricted search, or you can actually restrict a specific property. So, for example, if I give this search string on top of this after question mark and hit enter interactively, or just send this URL through a Python or an automated tool, it will send me a JSON file with all the compounds which have an ICSD number which are metal, in which in the unit cell uh, you have the compound has at most at least two different elements. In the unit cell, it has at most 12 atoms in the unit cell, and it will give us all of these extra properties, such as the atoms DFT energy, its space group, what kind of DFT was run to calculate this energy, a prototype structure, composition, etc., which can be seen on this side actually. So, for example, you have AL4 DY2. Uh, this is its AUID, a unique sort of number for each calculation that AFlow stores. This is the URL where you can actually directly go and search and get the details. And these are a skeleton of property that you requested. It tells that this is a metal, it is a binary metal, it has 6 atoms in the unit cell. These are the species, this is energy per atom, its space group is this. If we want, we can actually extract further more property. It just requires a little bit of processing. So, having learned that, we actually performed a search query for binary compounds, which are metal. One sort of a little bit of a drawback that it has, which is not really a drawback because it keeps adding each independent calculations. That is, uh, when you search for a compound, you find several duplicate entries, which you have to actually remove, and you have to write your own piece of code to actually remove sort of duplicate entries. So we did that and further divided this list into 3 subset. Basically, if M and D represent a set of main group element and a D block element, so a main group, main group, main group, D block, D block, D block. So these 3 set you can actually generate, and we get potentially a very large number of compounds. With this, we also get we can download, once we have the list of compound, their SPD and potentially atom resolved density of state. That's something which is going to be used for the as an input for our model descriptor. And this data is available through another query in a sort of compressed JSON format. Uh, Here we show illustration. So these 4 panels of the figures are all density of states. So the first panel is the actual density of state for chromium cobalt 3 chromium 1, some representative system. What we do is we actually fit this density of state to an actual semicircular one, which so this is the sort of fit that we actually produce. This is another compound, aluminium 1, arsenic 1, and the corresponding sort of the semicircular density of state. So we fit each of these data, because these are potentially noisy, to a appropriate semicircular density of state, from which we actually get the bandwidth and the center of the band, which we need for our model descriptor. So we did this exercise for the D block compounds. And before we go there, so let's just have a quick look on what kind of numbers in terms of material set we actually found. So in elemental, basically from main group, we had calcium, strontium, barium, uh, 27 prototypes, and something like 88 prototype elemental data from D block, 3D, 4D, and 5D transition metals. So these were the actual materials which exist and their corresponding crystalline form. Among binary, uh, so we were looking for MXDY and DXDY system. So we found something like 88 prototype in this and 600 prototypes in the DD, or a D block combination. One can now appreciate the advantage here, that if one had to calculate the surface bonding energy of a 650-ish prototype compound, that's an enormous amount of computational time given that one has to do surface calculation. However, with the model, one can estimate this energy just on a laptop. So we first start with elemental prototypes and use the fit parameter to actually get the binding energy. And here are the sort of the binding energy for elemental metals ranging from, so these are basically 3D, 4D, and 5D. So 3D, 4D, 5D transition metals are basically the first column, second column, third column in blue, green, and reddish. And these trends actually seem consistent with, I mean, so the 4D systems we had already fitted earlier. And this is a consistent with the 4D. However, I mean, this was calculated for many different crystal structures of the 4D compounds and also extended to 3D and 5D. And these trends actually are sensible. And it, among elemental, it actually already tells us what are the potentially reasonable candidate among the elemental data. When, and these are basically three. So the set 1, 2, 3. So these were the three sets of data that we had: the real structure, FCC force structures with surface density of state, and the third one with the bulk density of state. What we see is that qualitatively, these three data are not terribly different. There is a quantitative difference. So we choose of the data, let's say real data, the fit based on the real data, and just move on to binary compounds. For the binary compounds, one needs the not just the SPD resolved density of state. One also needs sort of atom resolved density of state, because we were using the hybridization of metal atoms with impurity. So the obvious choice of this VAD becomes ambiguous, and we need basically a scheme, uh, uh, some sort of average. We proposed a weighted averaging scheme to calculate the binding energy estimates of these binary compounds. Uh, so the next, and which we actually discuss next. Another issue that one actually faces is that when you have a binary or a ternary or basically an alloy, when you cut a surface, it generally has more than one possible terminations. For example, if you look at the plane 110, so this is a two-dimensional square lattice with rock salt art. Hello?
Yeah. Okay. Now you're back.
I think there is some sort of a bug. So when did you lose me? Actually, it keeps saying for some reason my internet connection is unstable.
Yeah. Same
Uh,
here.
uh, so where, at which slide my audio?
No, in this one here where you talk about binary.
Okay, so I will actually restart.
Okay.
Uh, okay, so yeah, so with binary, so let me restart again. So when we are looking at binary, uh, uh, we not only need the SPD resolved density of state, but the question becomes, so which one? Because a total SPD resolved density of state will have contributions from both binary components, A atoms and B atoms. And as a result, the choice of the hybridization VD becomes, so what do we do? And one possible solution that we have is that we need also the atom resolved as well as SPD resolved density of state to estimate the binding energy. Uh, in the next slide, we will actually discuss that. But uh, here I'm trying to just motivate that one needs some sort of effective averaging scheme that would be a cheaper estimate. And if we look at uh, this illustration, so what we find is that in binary, ternary, or otherwise compounds, Often, the surface cuts or the surfaces may have more than one possible and sometimes many more possible terminations. And each terminations may have a different distribution of surface atoms actually. So depending on what is the overall distribution, it provides an average. So it should show up as an average. Just hello. Oh my God, Stefano.
Yeah.
Just hang on a sec, Stefano.
Yeah. Sorry.
Uh, uh, where are you right now?
Here.
Uh, just just I'm coming down. Stefano, can we actually pass the? I mean, Stefania had ordered the this package from Dell, and the guy is downstairs.
Okay.
What should we
Um.
do?
Okay. Let's do this actually. Can you maybe let's okay, let's pause for a second. We
Okay.
start back in 5 minutes, in 10 minutes, okay?